Hello. So let's just jump straight to it. This is for week 2, and I'm going to start with this example. So if I were to just take an image of this right now, 1 second. Mm, example 3. Let's start with example 4. All right, so example 4 states, the zinc blende crystal structure is one that may be generated from closed packed planes of anions. Okay, so A, will the stacking sequence for the structure be FCC or HCP? Well, if we go to this computer simulation I found, this is a zinc blend, and the yellow represents the anions, which is the sulfur. And the main thing that I want you to notice with this one is, let me just get this Apple Pen out. Whoops, that's not working right. There it is, better. If we were to zoom in over here, so make this a little larger, we can see, if we look at one of the corner pieces, we can actually see how this structure is actually arranged. So in this case, one could say that this is the A. Let me just choose black here. So this is the A part. And then the layer behind that will be the B part. So B over here. And then the layer behind that one will be the C. So C, C, C. And if we were to go to the opposite end of this corner, we'll see that we'll have the exact same orientation where it's just A, B, C. And because we have 3 different orientations following the ABC pattern, well, if you remember from last lesson, oh, whoops. Sorry, let me just rearrange this so it's a little easier for me to work with. If we remember from last lesson, for example, 4, an ABC ABC pattern that correlates with FCC. So then because of this, we know that the anion packing will be an FCC structure. So then that's the first answer. Now moving on. Will the cations fill the tetrahedral or octahedral positions? Why or why not? Okay, so then for this one, let's go back to the original look of this structure. So then if I were to put the image up one more time, 1 second, let me just pull up the image. Change to reduce sphere. Better. Oh, no, 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 that's not what I want. Sorry, let me just pull up this image real quickly. Think that's a good, well, no, hold on. Sorry, I'm just like changing the angle positioning on my computer so that once I put that on the iPad, you'll see what I'm talking about. There it is. Use this photo. All right, let me just move this photo around. How do I move this photo around? Uh-oh. That's not right. God save the king. Is it this? That's not it. No, 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 that's not what I want. You know what? Okay, let me just erase this over here. And I'll rewrite that somewhere else. So then for A, this is a little messier of a session. Oh, wait, what? No, that's not what I want. On second thought, that is kind of what I want. Oh, oh dear. Oh, no, this is not going right today. Today is not my day. Anyways, but hopefully the image is large enough. And you can see that within this image over here, if you look at the interstitials, so in this case, the zinc, which are smaller atoms, I should choose a different color. Let's do red. We can see that the zinc is bonded to 4 different sulfur anions. So over here, over here, over here, over here, as indicated by the dashed lines which represent bonding. And on the slide, it's mentioned that there's a tetrahedral bonding for the zinc within the zinc structure. So then because of those clues, we can then determine that if I were to rewrite these, so let me just rewrite these over here, ABC, ABC, that correlates to FCC crystal structure for the anions. And then for B, well, because of the 4 bonds, that indicates a tetrahedral bonding. And therefore, the interstitials will then fill the tetrahedral positions because of the tetrahedron that they form. 4 bonds correlates to tetrahedra. Tetrahedral, which then correlates to filling the tetrahedral inter spots, positions. So then if it was octahedral, it'll then be forming 8 different bonds or 8 different dashes within the structure. But in this case, they only form 4. So then because of that, it's a tetrahedral filling. Going on to C, what fraction of the positions will be occupied? All right, so then when it comes to this one over here, we can kind of split this up into 8 different cubes. So for example, one way you could kind of imagine this is that if I were to draw a cube, I'm not an artist here. And then we kind of, so then we have a cube over here, and then we have the sulfur anions. I'm not going to draw them in for the simplicity of this. What we can actually do is that we can kind of split this off into 8 different cubes. So kind of something like this. Hopefully there's a clear. Boom, boom, boom. So something that looks like this. Let me just do the back as well. And then what we actually see is that when it comes to the bonding or when it comes to the zinc structure, if you go back to the slides, what we'll actually see, and I'll do this in blue, is that the zinc will only occupy 4 of these tiny, it'll only form or fill in 4 of these little mini cubes within this larger unit cell. So then let's just say for this one, it's inside this, one of them is inside this mini cube, another one is inside this one. Oh, there's also in the middle as well. So this one over here, and then the other one will then occupy this corner over here. And then the other one will occupy this one over here. This one. Hopefully that's clear. So then because of that, we have 8 mini cubes, but only 4 of them are occupied. So then because of that, only half of the interstitial spots are actually filled in. All right, so then that's for the 4th question or 4th example. Yeah, so not too bad, hopefully. So then let's go on to the 3rd example. So 3, what is the anionic packing crystal structure of fluorite? Explain your answer and be sure to include a diagram. Pardon me. All right, so then let's look. Oh, sorry, let's look at the question one more time. Okay, so fluorite is this one. So it's asking for the anionic packing. So then, oh, I can't draw it directly. Oh, wait, what? Nope, that's not what I want. Sorry. All right, so it's asking for the anionic packing. So then, first of all, let's just pull up a picture of a fluorite. So let me just, find that. Fluorite. There it is. Let's do, yeah. Let's do, how should I do this? trying to find the best way to angle it so that it's clear. Sorry about this. Oh, there. Yeah, I think this is clear enough. So, one moment, let me just bust out the camera. Hopefully, I'm not revealing too much of this. Yes. All right, so this is a picture of the fluorite. So then we see that the green is the fluorine and the purple are the interstitials of the calcium. And if we look at this, you might think to yourself, oh, okay, I'm looking at this and it might be FCC. And I wouldn't blame you for thinking that. I mean, look at the faces. This face over here is covered. I can't draw exactly on it. Can I? Yeah. So you see over here, these faces are covered. So yeah, I can see you thinking FCC. I can see that. However, when it comes to unit cells, especially when it comes to the specific packing, the main thing we really want to look at is we want to look at it at the most simplest form. So then if we're to break this down, and it kind of does that for us, we can look at the fact that this cube is kind of split up into 8 smaller cubes, very similar to the last example with the, I'm forgetting the name of it already. This is very disappointing. I'm forgetting the name of it. I'm drawing a blank. I've been on summer for way too long. Zinc blende, yes, sorry, zinc blende. And what we can actually do here is that we can apply the exact same logic. So then looking at this specific cube, which I'm marking in red, let's just look at this cube as like a simplification, a smaller unit of what we have. And we see over here is that it only consists of these atoms that I'm coloring in with red. So then if we look at this simplified version or this reduced form of a unit cell already, let me just erase the one in the back so I don't confuse you guys. We see that it actually manifests a simple cubic as opposed to an FCC. So then when it comes to these problems, always try to see if you can reduce it down to as much as possible. So then because of that, example 3 will actually be not an FCC, but a simple cubic. All right, so then that's for that one. Moving on to the next one. 23%. I gotta wrap this up quickly. So let's just go into the next. Take a photo. Uh, oh my gosh, not this again. I have not figured out a way to move images around. This is oh no. You know what? It's okay. Whatever. I'm not very, as you can tell, I'm not very good with the iPad. Hopefully, as time progresses, I do get a little better. Hopefully, though, that's a big hope. All right, so let's look at example 1, shall we? Uh, all right. All right, so example 1 states, given that the ionic radii for magnesium cation is R equals 0.079 nanometers and the ionic radii of oxygen is R equals 0.113 nanometers, you determine the crystal structure of MgO and draw the ceramic unit cell. Be sure to label the ions and justify your answer. All right, so this is a classic, like, okay, we know the ionic radii. Let's figure out the coordination number. So then when it comes to this, we should know, well, it's given to us that the cation is Mg2 plus and the anion is O2 negative. So then the general formula, let's do this in red, is Rc over Ra. So then if we plug in those values, wait a minute. Oh, that's strange. 0.079. I wrote down 0.089 or 0.088. It doesn't really matter because the number is roughly the same. Because remember, when it comes to these coordination numbers, it's a range as opposed to an exact number. So I'm just gonna pretend, yeah, I'm gonna give a correction for this because I'm a bit of an idiot. So note, RC is 0.088 nanometers. The process stays the same. It's just changing up the numbers. And RA is 0.130 nanometers. So then looking at this, we can just plug and chug. Nanometers divided by 0.130 nanometers. And then we see that this equals to 0.677. So then this is in between. So then this value is in between 0.414 and 0.732. So then this specific range, if you go back to the slides, correlates to a coordination number, so Cn of 6. So then because of this, oh, whoops, oh my goodness, that's all right. So because of this coordination number of 6, we can say that the MgO structure takes on a rock salt structure since the RC over RA ratio is in between 0.414 and 0.732, which is a coordination number of 6. So then going down, if we just start drawing this, and I'm realizing I am not the best artist, so bear with me. I'm going to draw a cube. So let's start this outline in black. No, 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 no. All right. And then I'm going to assign colors. So then let's just say green is the oxygen anion. So I start coloring those in. So then remember the rock salt structure is like a double FCC. So the anionic packing will be FCC. So then I'm going to draw that first. And then back over here. And then when it comes to the cations, it's essentially that at every single edge of this cube, you're going to find in the middle of the edge of the cube the cation, so Mg2 plus. So then this is your rock structure, or rock salt structure. Yeah, so essentially like that. Hopefully you guys can draw better than me, which you guys probably can, but that's my best attempt. Obviously not an artist, so, but hopefully it gets the message across, and that's all that matters to me. So example number 2. So example number 2 says, you're given that the crystal structure of cesium chloride is the cesium chloride structure. Shocker, I know. What is the cationic coordination number given that the anionic or ionic radii of CS plus is R equals 0.165 and the ionic radii of chlorine is, or chloride I should say, is R equals 0.181 nanometers. Be sure to justify your answer. So again, very, very similar to the first example we did with the rock salt MgO. It's just applying the formula again. So 0.165 nanometers for the cesium and 0.181 nanometers for the chloride. That correlates to 0.9112. And if you go back to the slides, we see that 0.1912 is in between 0.732 and 1.0. So then because of that, we see that it has a coordination number of 8. Yeah, so then the justification that you kind of write here is that due to the RC over RA ratio being 0.9112, the coordination number is 8. So that answers that question. Let me just make sure I got that correct. Yeah. What is the cationic coordination number? Yeah, it's just taking the ratio of that. All right, next batch. So then I did 1, 2, 3, 4. Let's see what else I need to do. 5, not that. 6, I do. 7. Okay, so 2 more. So not bad. Not bad, not bad. I'll take that. So, sorry, let me just editing my doc so then I can just take a clearer picture. There it is. Oh, because it's a little small. So then let me just take this picture right now. So take a picture or video. Uh, there it is. All right, so using this photo. So this is example 6 because example 5 is was it for next week? So I'm not going to do it in this video. So example 6 states, on the basis of crystal structure, compute the theoretical density for sodium chloride. How does this compare with its measured density? Hold on, before I do this, let me double check this is still week 2 and not week 3. Because I had a bit of a spacing problem. So let me just double check. Okay, it is. Okay. Just had to double check. All right. So we're going to that thing. All right. So then going back to the slides, we know that the formula, I'll do this in yellow. So the density formula is NC times AC plus NA AA all over VC times NA, where NC and NA represents the amount of atoms that we have inside this unit cell. AC and AA are essentially the atomic weight. VC is the volume, and NA is Avogadro's number. So we know what NA is. That's just Avogadro's number of 6.022 times 10 to the 23. AC, so the atomic weight of the cation is going to be 22.99 grams per mole. AA, atomic weight of the anion, is going to be 35.45 grams per mole because this is chloride. And is there anything else we need to figure out? All right, so the next thing we should figure out is what is NC and what is NA. So let's figure those out. So then if I were to pull up an image of a rock salt structure, actually, we can just use the rock salt structure I drew over here because it's going to follow the exact same structure. NaCl and MgO, as proven by the fact that inside the I think on the slide I showed that NaCl has a coordination number or cationic coordination number of 6. That's the same thing as MgO. So then we can actually use the structure. And if we know anything from an FCC structure, we know that each FCC structure has 4 atoms inside. So then because of the anionic arrangement of a rock cell structure being FCC, we can actually say that the anionic or Na will actually be 4 because of that fact. So then if I were to just scroll down, we can then say that Na is equal to 4. Now, what about NC? What about NC? So then going back over here, so then when it comes to this over here, let's count out how many corner pieces we have. Or actually, hold on, let me just pull up a better image. Or actually, no. 1, 2, 3, 4. Well, it's just better if I, for the sake of example, let me just pull up an image. So rocks, rock cell structure. Yeah, okay. So this is a lot better. That's what I wanted. So let me just take a video of this. This is what I'm gonna use the photo. So then if we look at kind of like a full complete view of an FCC structure, we see that it kind of looks like that. So then if we count up the amount of, so the purple represents the Na plus, while the green represents the sodium chloride or the chloride, which we already figured out Nc to be 4. So then let's figure out the amount of sodium ions we have. So then if we were to count things up, or we look over here, we see that each of these pieces over here, each piece over here represents 1/4 of an atom. So then if we start counting up over here, we see 1, 2, 3, 4, 5, 6, 7, 8, 9. And then there's going to be 10 to represent this side, 11, and 12. All right. Am I forgetting one? Am I forgetting one? I feel I'm forgetting. Oh, wait, actually, hold on. What am I doing? Sorry. This is not very organized. I apologize a lot for that. Let's just count out the amount of cations, full spheres that we have. Because we know that each cation will take on this like orange wedge type shape, which represents 1/4 of an atom. So then let's just count out how many of these we have. So then we have one, oh, sorry. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so then we have 12 of those orange wedge things, and each wedge represents 1/4 of an atom. So then if we do some math, then we do this. Yeah, let's just do this here. So 12 times 1/4, that's going to give us 3. Okay, but we're not done yet, because if you look at the center atom, this center atom, because it's inside the middle of this entire structure, it's not going to get cut off. So then it's not going to have that orange wedge shape. Instead, it's going to have the entire atom. So then that's just one whole entire atom. So then that's going to be 3 plus 1 gives us a total of 4. So then because of that, we know that Nc, the amount of cations within the structure, is also 4. So then if we start plugging in through the formula, we see that density is equivalent to N, oh gosh, okay, again, 22.99. I'm going to skip the units because you know what those are. And I'm running out of batteries. Oh my goodness, I have to do the units or the volume as well. Well, on the slides, you will see that because it follows an NaCl, which is pretty simple, and I gave you the formula for that one, Vc is equivalent to 2 times R1 plus R2. And R1 plus R2, that's just the sum of the ionic radii, and it doesn't matter which order you put them in because it's addition. The order does not matter. And everything is raised to the 3rd power. So then whatever that value is, once you plug that in, multiply by 6.022 times 10 to the 23rd, that comes out to 2.14 grams per centimeters cubed. And when it comes to the volume, be sure to use centimeters, or else you're not going to get the correct units, and therefore not the correct value. On 10%. All right, last question. All right, 10%. Okay, last question. All right, let's do this. Oh my goodness, this is the longest one. Oh my goodness. I did not, this is not a good session. And I'm starting to lose my mind a little bit. And everything is just circling, spiraling. Okay, 7. So the following table lists diffraction angles for the first 3 peaks, first order. So first order means n equals 1 of the X-ray diffraction pattern for some metal. So monochromatic X-ray or sorry, X radiation having a wavelength of 0.0711 nanometers was used. So A, Determine whether this metal's crystal structure is FCC, BCC, or neither, and be sure to explain the reason. Okay. So when it comes to A, we're going to use Bragg's law. And because we're given that as a first order, n is going to be 1. Let's do this in blue. Slowly losing my mind. So Bragg's law will be n times lambda, which is equivalent to, oh my gosh, 2 interionic spacing sine theta, where n is equal to 1. All right, so then let's rearrange this. So then we get the interionic spacing. So that's going to be lambda 2 sine theta. And when it comes to this, the logic that we're going to be using, oh, and also was it, we're not going to do B because I don't have table 3.1, so skip B. I don't care about B, we're just going to do A. And when it comes to this, if you're given data about the FCC and the structure and all that, then sure, you might be able to do it, but I don't have that extra information, so we're not going to concern ourselves with that. We're just going to do A. So the main, the main strategy for this one, sorry, let me just pull the notes to make sure I'm not missing anything. Anyways, yeah, so the main strategy, I should have mentioned that soon. So the strat. So the strat is determine DHKL or DKHL for each reflection to use DKHL to find A. A, remember, is the last parameter. And then for 3, oh my gosh, no. I'm losing it. Seriously losing it. 3 is going to be see if A is consistent. Because if A is not consistent, then that is not the correct crystal structure. If A is pretty consistent, then that is the correct crystal structure. So then let's just go ahead and do this. So we have this over here, and let's just figure out the different peaks. So remember, if you remember the reflection rules, we should know that if this thing is FCC, the first 3 peaks should be 111, 200, and 220. If this thing was BCC, then we should know that the first 3 reflection points should be 110, 200, and 211. Okay. So then let's just figure out the different peaks. So then peak 1 would become DHKL is equivalent to 0.0711 nanometers divided by 2 sine. And remember, this is very important. This is really important. Don't forget this. Notice how the image says 2 theta. However, inside Bragg's law, it's theta. And what we have to do is that we have to take the value of 2 theta and divide it by half in order to figure out what theta is. The reason why it's 2 theta, remember from the last video, is because, because of the specular reflection, the angle of incidence will be equivalent to the angle of reflection. So then they just put 2 theta as convention. So don't forget to divide by 2 if it's 2 theta. So then following that, that's, what was it, 18, what was that value again? It doesn't matter. That 18 point whatever it was now becomes 9.133 theta or degrees. So then this becomes 0.223. Oh my gosh, 2239 nanometers. And following this exact same pattern for all the other ones, I'm on 5% battery right now. I'm so sorry. Very scuffed. And if you have any questions, it's okay. You can just contact me. Because this is my fault. I'll just give you the values right here because it's the exact same process. Just exact same formula, just different angles. So then we have these values. 1293. nanometers. Okay. All right. So then knowing that, so knowing those values, let's check BCC. Let's check BCC first. So when it comes to BCC, the last parameter, sorry, I'm blanking out. Why am I blanking out now? Oh, sorry, yeah. So when it comes to the BCC, well, everything will be a cubic structure. So then that's going to be HKL is equivalent to H squared plus K squared plus L squared all over A squared. Okay, so then looking at that, let's rearrange it so that we can get A squared by itself. Or not A squared, A by itself. So then what we actually get is that we get D HKL, and then we have H squared plus K squared plus L squared. Okay. All right, so then over here, what we now do is that if we know was it going back to what we said about BCC, the first three peaks should be 110, 200, and 211. So essentially what we do is that, for example, I'm just going to do an example with peak 1, but it's the exact same process with the other peaks, so peak 2 and peak 3. What we actually do here is that for the last parameter for this one, we do D1, which is going to be 0.2239 nanometers multiplied by the square root of 1 squared plus 1 squared. So it's taking this over here. Just remember, this is the H, this is the K, this is the L, plus 0 squared. And what we actually get is that we get 0.3166 nanometers. So then if we were to follow for the other peaks, we get values of 0.317 nanometers, and peak 3 is 0.3167 nanometers. So notice how similar these last parameters are. And because of this consistency in the last parameters, therefore, we can say that this structure is a BCC structure. So this is a BCC structure. Because of the consistency in the last parameters when we plug in the values for a BCC structure. If we were to do this for an FCC, we will get values of 0.3878 for peak 1, peak 2 for FCC will be 0.3166. I'm sure write these down. So 1 would become 0.3878, 2 would be 0.3166, and peak 3 will be 0.3657. Notice how all these are super, super different. So therefore, it cannot really be FCC. So BCC is the better structure, and everything is going to die. Thank you, goodbye, and hopefully I'm alive. Bye, thank you.